Hello and welcome back to this course on fundamentals of data science. And today we have these two parts, training data and learning rate. In fact, we are going to observe what is training data and how we can actually train a system. We are going to see step-by-step process. In the same time, we are going to see how a small change that you make in the system to improve your performance, eventually it's called as learning rate. We are going to examine these two factors in today's lecture. Let's start with some basics. Here it is, a simple predicting machine. So just imagine that you have this system, it's a kind of a linear system, and from your observation we come to know that kilometers and miles are linearly related. In other words, whenever you increase the kilometer, it will also increase the miles. So with this thought, we can actually perform many simple tasks. Let us take some true values, and based on the true values, let's try to train this system. Well, one of the true values that you have is, let's say we can call it as truth table if you want, because I'm going to call it as the true examples, in which for the first time, for the first example that we have is for 0 kilometers you have 0 miles, and for 100 kilometers you have 62.137 miles. So with this true values, you are going to see how we can actually train the entire system. So that's the beginning stage. So with this thought in mind, let us see how we can examine the entire scheme. You know that miles equals this part, the kilometer, times this value, some value you have, say let's call it as C. So with this thought, we will try to examine what is this C value. Let us try to put the C value to be, say, 0.5. So miles, let's call it as m equals k times C, and if C is 0.5, what happens? Let's take it as m equals k times 0.5, and in fact we can consider this whole scenario as, say, you have 100 kilometers, and then you are going to have say this is miles equals kilometer times 0.5. In other words, here you have this 0.5 has been multiplied with the kilometers. So what happens to the miles? Miles becomes 50 right now. So with this thought, can you see what is happening here? As we can see here, the original true values that we have for miles is clearly given. For the first one, 0 kilometers, 0 miles. For the second one, 100 kilometers, it's 62.137 miles. So right now there is an error in our predictions. We initially started with 0.5 for C, and then we got 50 as our answer, but the error is true value minus the calculated values. In other words, it is 62.137 minus 50, which is 12.137. So that is our error at this moment. So with this error, in fact with this error we can come to know that we have to refine a little bit so that we can improve the entire system, and we get the 62.137. Well, initially we took C as 0.5, C was 0.5. How about if you improve the C to be 0.6? What happens? If C is 0.6, then miles going to be 100 times 6, which is going to be 60. So again, the same thing, it's going to be 60. So in this case, what happens right now when you have such scenario as 60? Well, right now you can calculate the error and see what happens. So when you try to calculate the error for 60 with C as 0.5, you come to know that the error is 62.137 minus 60, which is 2.137. Of course, we have improved this error a lot. We have reduced, in fact, reducing the error from 12.137 to 2.137. With the same line of thought, you can also think about what other things that you can do to reduce the error. There are few things that we have to be careful in this regard. At times we might be increasing the error. Say we already tried C as 0.5 and we tried C as 0.6. So what happens if C is chosen as 0.7, for example, or what happens if it is chosen as like 0.8? How are we going to deal with it? Let's say we take C as 0.7. What happens when C is taken as 0.7? You will get the answer like say 0.7 times 100, which is 70. And again, if you check the error here, 62.137 minus 70 equals minus 7.863. So at this stage, though we have reduced the error a lot, now the error is increasing again. Since the error is increasing, we call it as an overshoot. This is termed as an overshoot. So we have to make sure that we will never go into this scenario. In fact, we want to make sure that the error is minimized after each and every step. So in order to do that, the better option is that we can choose a value which is slightly more than 0.6. In this case, we can choose, say, C equals 0.62 if you wish, or 0.61. So if you choose 0.61, what happens? The values would be 0.61 times 100, which is going to be 61, and your error is going to be, it's going to be like 62.137 minus 61, which is 1.137. Well, we have seen that with 0.61 we have in fact reducing the error. Initially, if you look at our values, for each value we had some errors. Like initially we talked about 12.137, then we had 2.137, right, and there was an overshoot we had like 7.863. Then now we reduced the error by 1.3, it's 1.137. So this is the effort that we are making. We are trying to reduce and change and the values of C, and if the output is getting closer to the correct answer, we try to reduce the error slowly. Small values are changed a little bit, and then you are trying to achieve this entire task. So as we have done this 4-step, say let's call 1, 2, 3, 4 step has been done. In fact, you would have skipped the 3rd step if you wish, because it is not wise to make a big change when the errors are reducing. In fact, this steps that we are doing it repeatedly again and again, we call it as the iteration, or in other words, it's an iterative method. So this is one of the terms that we would come across, how the iterations, several iterations we do to achieve a simple task. Well, with this same line of thought, let's try to understand how we can perform from predicting to classification. We see this prediction is just similar to the linear predictions that we talked about in case of a linear regression, and later on we also talked about classification method. A simple predictor is not a classifier, it's a little bit different. The outputs that we get is a classification of two objects instead of predicting a parameters. So in the previous example we saw that we are trying to predict the value of C, right? We try to predict what is C, but this example that we are going to see here, where you can see there are two categories, one is a caterpillar, the other one is the ladybug, and the width and length of these bugs are given to us. So based on that we are going to understand and see how this can be classified. Again, remember the predictor that try to work out the correct number, in our case the correct number of miles for a given kilometer. So that predictor had an adjustable linear function, it's kind of linear function, linearly it is changing, because whenever the kilometer changes, the miles also changes. Yes, that linear function gives a linear straight line for us, but when you plot the output against the input, you can see actually there is a straight line coming up in that case. So that adjustable parameter C changed the slope of the straight line earlier. But here we have again, if you try to put some straight line, what happens? So we have to see how and where the straight line can appear, and this straight line, unlike the predicting straight line, it has to classify. Perhaps it has to separate the two different kinds, in this case caterpillar and the ladybug. This type of dividing the two kinds, we call it as a classifier or classification. So in this case we are going to classify different bugs. Say for example, if you have a straight line just like here, does this straight line classify the two bugs? Definitely not. How about this line here? Does it classify? No, it doesn't. So the first line we have drawn, it grows across the caterpillar, which means some of the caterpillars are also part of the other category, and the second line we drew, which does not cross into any of those things and doesn't divide either. So everything has been changed as one class. So what is expected line that can separate? Yeah, this would be the expected line that can separate correctly. So we can call it as a classifier. So it classifies any bugs that comes in. So if you have a new bug coming in, and if you have a new bugs coming in, it has to able to classify whether this new bug or an unknown bug as a ladybug or as a caterpillar. With this thought, let's try to understand this training process, this whole process of training. So we can call it as the training a simple classifier. So we want to train this entire system again, like the previous one. Now we got with some true values. So this is kind of a truth table, I could say, but in fact this is the true values that are given to us, in which the width and the length of the ladybugs are given to us, and width and length of the caterpillar is also given to us. So with this thought, we are going to proceed and see how this whole scenario is going to work out. So we know that here from the given part. Ladybugs and caterpillars are given, so we have to understand how we are going to come up with this particular line. So we can go back to the simple straight line equations. So we know that y equals ax plus b, and we don't want to make it more complicated, but we will just take it as y equals ax. We assume that the line processed through the origin, and we don't want the constant b right now. So with this y equals a times x, we are going to proceed with this process. Okay, let's consider the values for a. What is the value for a? We have to start with a random value. So for example, if you have y equals 0.25 times x, what happens at this moment? So we are having this training example, and then we are trying to understand how this is going to be drawn, where y equals 0.25 times x. So is this a right classifier, y equals 0.2 times x? So we have to understand whether it is actually helping us to improve this whole process. I will come back to this slide to understand how this affects the whole process of this error factor. So right now you can see, if you try to draw that line, this goes somewhere over here, y equals ax, which is 0.25 times x. And if you look at the values of width and length, you have width in your x axis and your length in your y axis, and if you see closely what is happening there, y is 0.25 times the value of x, and the ladybird width is 3 there, and the length is 1 there. So we want to make sure this y equals 0.25 times the x value, which is equal to the y, and in this case the y is, to be precise, the y is around like the y is in fact is 1 actually. If you look at here, the length of the ladybug is 1. So we want to make sure that this equation y equals 0.25 times x should go beyond this ladybug. So we want to make sure this happens. We want y to be more than this value. So you can adjust. Now you can take another value for this y. So let's take y as, say, 1.1. If y is 1.1, as we can see here, if you take the y as 1.1, you might come up with an error. So there are two things. Initially, we found that if suppose you are going to have the same equation where y equals 0.25 times x, where this is going to be 0.25 times 3, for this is 3, x is 3 for ladybug, so that is going to be 0.75. So y is going to be 0.75, which is in fact the line actually goes down the ladybug. But we want to separate these two bugs or two kinds of things. In order to do that, we need to improve it. What is the best value for y? That's where the question comes in, and we have to make sure that it goes beyond the ladybug. We don't want y should not be 1. So let's take y to be, say, 1.1 or 1.2, for example. and you don't want y to be 100 also, like it will be completely out of the graph. So with this thought, let's take y as 1.1. So if you take y as 1.1, that's where this comes in here. The desired value is 1.1 and the calculated value is 0.75, right, and we are trying to calculate. So this is the previous one, the y equals 0.25 times x, which is in fact we put the x as 3, so y equals 0.75, and the other line that we come here is y equals 1.1. Well, with this thought in mind, we can see there is an error actually happening here, right. So the error is 0.35. So the actual error that we got is the 0.35. This is what we have to make sure we improve this value, the original to the original values. So accordingly, you make sure that the initial value y equals 0.25 times x was there, and refined value where y is 1.1, here y was 1, here y in fact it was 0.75. So likewise you can add up, or we can try to introduce new values for y. So this whole process of trying to understand from the beginning, we are actually calling it as training the system. We are training this entire process step by step from the beginning, and as we train this from the beginning, we come to know that we are actually trying to classify correctly, but this is done step by step. The whole process has been done step by step with the simple training classifier, and finally we come up with this refinement here where y equals 2.9 times x. That's 2.9 times x is the final refinement you are getting up. So likewise there may be many other lines, right. You want to make sure you get a correct line for y equals certain values. So this process, this whole entire process in which we are iteratively doing step by step process, this is a little bit different from the predictive methods or predicting missions that we talked about earlier with respect to kilometers and miles. This is the actual simple classifier, and right now what we are trying to understand is that we are trying to understand how this training process is happening and how this actual learning rate is happening. So when I say learning rate, we have to understand that once it is 0.75, we know that 0.75 is not a good classifier. So y value cannot be below 0.75. So we have increased to 1.1 in this case, which is pretty good. And finally we are coming up with some more values here and here, and at this time we have struck with this one, final refinement, which is also quite good for us, with y is equal to 2.9 times x. But beyond this, if you go beyond this somewhere here, which is not a good value. So this is in fact give us a different view of matters with respect to how the training is happening and how this training system can help us to understand the learning process. So the learning process here is that we try to understand this point and this points are not feasible points definitely, and of course we don't also want points over here which is close to the bugs. We want to clearly separate these two categories very distinctly. That is the actual objective of the scheme. So here is what we have. So the final moderate, so we call it as this updation, the updating of values, we do call it as a moderate or refinement. The refinement process is happening, and we don't want this, or we don't want another one which is so close to the actual kind or the bug, but this one at the center, which is quite good and straightforward, is our actual values that we are looking at. So whenever we do a process, whether it is a predicting machines or a classifier, though both of them have two different approaches, but we can see that we go by step process in increasing the weight a little bit, a little more, it gets closer to the final output. So that's what we discussed today. We talked about training data, and we know that how for a predicting machine, in our examples we saw that we change the training process iteratively. After several times we repeatedly do the things again and again, so that our error is minimized. In the same process, we also understood how this can be used in a classifier, wherein the actual learning process happens as we reduce the error, and it classifies the two kinds more precisely. So that was the discussion for today's class. And what are we going to look at in next class? In our next class, we are going to discuss about the introduction to graph theory and applications of graph theory with respect to data science. And we'll start with the so-called minimum spanning tree. So that will be a discussion for next class. I'm looking forward to see you there. Goodbye.